we have completed module 1 and now we are starting module 2. Okay, so under module 2 we have plastic deformation, mechanism of plastic deformation, and anisotropy, flow rules, and some other important topics. So which are important, to discuss in order to better understand your metal forming processes. Okay, so we will be talking in detail about metal forming processes one by one from module 3 onward. But module 1 and 2 covers your, elementary knowledge required to understand your metal forming processes. Okay, give me a second. Okay, so let me come to the first topic in module 2, that is elastic and plastic deformation. So from the beginning, that is from the starting of module 1, we are discussing about your elastic plastic deformation in metal forming processes. But we will be more, detailing about elastic plastic deformation. We are aware, maybe you might have studied most of the component of this course in your previous courses like material science and manufacturing processes. Okay, so some kind of repetition you will find, but it will definitely enhance your knowledge in this particular area. Okay, so let me repeat it again about what is elastic and plastic deformation. Okay, so let me ask one thing. I wanted to know whether you have done, any tensile test in your past classes, like in laboratory or any other place, wherever you have carried out tensile test. Have you carried out any tensile test?
Yes, sir.
In which subject and
Strength of material lab.
Okay, very good. So I was expecting this, that it might have been carried out. You might have, might be aware about the tensile test processes, how it is carried out, and what are the outcome of your tensile test. Okay, so you might be aware about the homogeneous deformation, and that is new term, or maybe you might be aware during your tensile test. What we expect, that the deformation in your material should be, uniform deformation or homogeneous deformation. So those who do not recall or do not remember, for them I am reading it again. Homogeneous deformation or the uniform deformation refers to the state in which the magnitude of your deformation has the same value for all material point in the sheet metal. Okay. So let me take, to your back. Where did you carry out your tensile test? You might have prepared this kind of specimen, and this is the gauge, length which is under observation, and you are trying to compute different material properties using this tensile test. Okay, so in homogeneous deformation, the important property for carrying out your tensile test is that your material should be deformable homogeneously. It should deform homogeneously, or the deformation at each at all points, all material points in the sheet metal has the same value. Okay, so we prepare such kind of test specimen and which is clamped on a tensile testing machine. Okay, and you get this kind of curve. We have iteratively discussed about tensile tests. We get these kind of curve when we this kind of curve when we compute your stress values on a graph paper. Okay, so this we are aware that O to A is your proportionality limit. Then sorry, O to A is your proportionality limit. Then O to B is your elastic limit. Then Y is your yield point. Then M is your ultimate tensile strength, and F is your fracture point. So these are the this is the curve which you normally obtain from uh, a tensile test. Okay. Yeah. So till now, how we are defining your for your tensile test, how we are defining your strain? We are defining your strain in terms of your original, in relation to your original length of your test specimen, or your initial length of your test specimen. Okay, so this strain is called engineering strain, and it is normally defined as epsilon n, or sometimes it is written as E engineering strain. E is equal to your final length subtracted by your initial length divided by your initial length. Okay, so this is nothing but change in length upon your original length. Okay, so let me come here. In engineering strain, you have a test specimen. Suppose this is your length which is under observation, and you are having certain length LO. Okay, and expecting that the deformation in this particular strip is homogeneous, that is the strain at all points has the same value. Okay, so it is getting the length of this test specimen is getting increased by a value delta L, and your length becomes L1. Say L1. Okay. So how we will calculate engineering strain? This will be L1 minus LO upon L. Okay. LO. Okay. So this is given as delta L over L. This is, now we are aware about your process of calculating your engineering strain. Okay. In this simple case, what we assume that the strain has the same value for all points or any point on the strip. Okay, so the strain value on each point is having the same value. It is not like that at some portion the strain is more, and at some portion the strain is small. It is not like that. The deformation in the metal is uniform, and when you try to see when your tensile test, if the force has exceeded your yield point strength. Okay, so what is happening? There is some kind of plastic deformation is all exists in your metal strip. Okay, so this not only plastic deformation, there is elastic deformation is also there. Okay, so when you remove your load from your metal strip, what happens? It regains some of your portion get get its original position. It's trying to get its original position, but there is some permanent deformation because it has exceeded your yield strength. Okay, so in a test specimen during the tensile test, when your force has exceeded your yield point value, what will happen? There is elastic strain as well as your plastic strain. Okay, the elastic strain. What is the elastic strain component? The strain under load consists of elastic strain, which is a recoverable part of your total strain when the force is removed, and the plastic strain, which is unrecoverable part of your total strain. Okay, so when we are in your tensile tests, when we are suppose a test specimen has reached up to this point. I'm pointing out using a mouse. Okay, so suppose it has reached to a certain this point. And when you are releasing your force, what will happen? It is not coming to your original shape and size. Okay, so it is, there is some kind of permanent deformation, and there is some kind of elastic deformation. Okay, so due to elastic deformation, material is trying to regain its near to original position, but it is not reaching to the original position. Okay, so this is because since there is some plastic deformation, and material is not able to get its original shape and size because of plastic deformation. Okay, so let me move ahead. Okay, so in this tensile test, what we see there is in your total strain, when we are calculating your Ising strain, there is elastic deformation as well as plastic deformation. So elastic deformation is recoverable part. The material is able to recover, but the another side, that is the plastic strain, it is the unrecoverable part of your total strain. So in writing your total strain, we may write at total strain epsilon n is equal to elastic strain, that is epsilon EL plus epsilon PL, that is summation of elastic deformation, elastic strain and plastic strain. In sheet metal forming processes, talking about where your metal strip or sheet is exceeded your yield strength, your elastic strain is much smaller than your plastic strain. Okay, so normally when we compare your elastic strain with your plastic strain, your plastic strain is much higher than your elastic strain. Okay, so that is why at some cases, or normally in the case of sheet metal working processes, we only consider your plastic strain. Okay, why we only consider plastic strain? Let me elaborate more. The elastic strain are in the order of 10 to the power minus 4. Okay, whereas the plastic strain are in the order of 10 to the power minus 1 to 10 to the power 0. Okay, so you can see there is a huge difference in the order of your elastic strain and plastic strain. So the plastic strain are much lower, and normally they are they are not considered when we are considering plastic strain, or when we are considering the total strain in your sheet metal forming processes. Thus, we can conclude that your elastic, your total strain can be given by, because it is nearly equal to your plastic strain. Okay, and why it is so? Because your elastic strain is much less than your plastic strain. Okay, so this is how we eliminate your elastic strain part in your sheet metal forming processes. Okay, so let us try to understand more what is happening in the case of your Ising strain when we are trying to compute your Ising strain. What are the issues, and how this concept of true strain has come. Okay, so let us take one example, that you are having a metal strip. Let me draw here. Okay, it is already drawn. We are having a metal strip. Initial length LO, and after the elongation, your length of your strip becomes L1. Okay, so final length of your strip is L1. Okay, So if you want to calculate your engineering strain, this would be L1 minus LO upon LO. Okay. So this will give you a the value of your you know total strain, or you can say if you are considering it's equal to your plastic strain, because the elastic is the order of plastic strain is very low. So we can say plastic strain or the total strain is equal to L1 minus LO upon LO. Okay. So what is the issue? Let me read. The engineering strain measure is not appropriate for large plastic strain, because the engineering strain cannot correctly describe the extension and compression of strain. It cannot describe sequence of deformation properly. Okay, so let us try to understand why it is not able to describe deformation properly, as well tension and compression tension compression test properly. Okay, so let me erase all. Okay, so take case one. Case one is your tensile test. Okay, in tensile test you are having a strip, say length L. Okay, and what you are trying to do in the case one, you are stay a second. This is your original strip. Let me write original strip. This is your original strip, which is which needs to go under tensile and compression test in order to see the homogeneity. Okay, so suppose you using your tensile test, what you have done, you have stressed it to a value which is twice of your initial length. So your initial length was LO, and now your length is 2LO. Okay, so this value is 2LO. This is the case one. That is the tensile test. Okay, case one. Let us take case two. We are compressing this your metal strip. So obviously, since we are compressing, suppose we have compressed this metal strip to a value which is equal to half of your original length. So now your length becomes LOY 2. Okay. So try to see in the case one, what will be the change in length? Change in length will be final length, that is 2LO minus original length. Original length is LO divided by original length. So in this case, your engineering strain will be 2LO minus original length LO divided by original length. So this will be 2LO minus LO. So this will become 2L minus L. This will become single L divided by L. So this value will be 1. What will be the value of the strain? Here it is coming equal to 1. While in the case of compression test, what is coming? Final value of your final length of your test specimen, it is LOY2 minus original length LO divided by LO. So when you subtract it, it will come minus LOY2 divided by LO. So what is the value in this case? In this case, your final length subtracted by your original length upon your or original length. Okay, so what will be the strain value? This will be minus 1/2. Okay, so uh, let me let's try to see it. So here what we can see in the case of tensile test, your is this value that is tensile test value was tensile strain is coming 1 for the same ratio of length elongation, but when we are compressing your test specimen, the how much value is coming, we could expect that since it is 1, this value may be minus 1. Okay, but it is not like that. How much it is coming? It is minus 1/2, so it is minus 0.5. It is minus 0.5. Okay, so we can see the last the ending strain is not uh, true measure. It cannot measure true strain sorry, true strain in the case of tensile and compression. Okay, so but what it should be, actually we were expecting that when we are giving same area same length reduction, it should be, when we are elongating, it should be positive, and when we are compressing, it should be negative. Okay, so in true strain, what we can expect that it should be 1 and it should be minus 1. Okay, or something like that, but it is not happening in the case of your engineering strain. Okay, so in the tension, what it was coming, it was coming epsilon equal to 1, and in the case of compression, it is, sorry, it is a typo error. Actually, I have typed this PPT in yesterday's night, and I couldn't check it for revision. So it is not 5, it is minus 0.5. Okay, so in the compression uh, test, your elastic is, your total strain is coming 0.5. Okay, so this way we can see the ending strain calculated for tensile test as well as compression test. They are not symmetric. They are not showing any symmetry. They are asymmetric, and and with the use of engineering strain, you are not able to estimate plastic deformation in complex conditions. Okay, so that is why we go for engineering strain or the sorry, true strain. Yes, anyone asking any question? Somebody has unmuted his mic. Haris, do you want anything? Do you want to ask anything? By mistake, let me mute it. If you want to ask anything, you again got unmuted. Okay. Okay, no problem. So, yes. We were here. Okay. So suppose in order to get exact value or the true value of your strain during your tensile and compression under the condition of tensile and compression, what we are trying to understand, we are trying to compute your instantaneous true value of your strain. Okay, so let us compare how this ending strain and true strain are being calculated. Let us take one small sip of your metal strip. It is having length some L. Okay, so In calculating ending strain, what we are doing, we are computing for a small strip DL over LO. It is being computed against your original length of your metal strip. Okay, so for any small elongation or the change in length, it may be written as DE equal to DL over L. So in order to calculate the total strain for the total change in length, that is from LO to L1, we can integrate this this strain, that is DE over the integration limit. You can say 0 to E. E is your true strain at the length of L1. So we can integrate this LO to L1 DL over LO. So you get this term, that is L1 minus LO in the case of your engineering strain. Okay. Now try to see the true strain. In the case of true strain, it would be say D epsilon is equal to DL over L. Okay. So what is L here? Suppose this is your metal strip of initial cross section L, and it has reached to a value L, and you are still applying some forces. You are trying to increase the length of your test specimen. Okay, so suppose at a particular moment for a very short period in very small element, we are taking, when we are applying force, there is some small elongation, that is DL, and we are calculating the strain DL divided by your instantaneous length of your metal strip. So this is how we are calculating your true strain. So instantaneous increase in length divided by your instantaneous length of your metal strip. Because now we are not considering your strain as compared to your by considering your initial length of your test specimen, we are calculating your true strain by considering your instantaneous length of your metal strip. Okay, so any change in length, suppose DL, we are calculating your small strain, that is D epsilon is equal to DL over L. And if you want to compute your metal strip, the total strain in your metal strip, then we may write it as D epsilon. D epsilon is equal to L integration from L to L1, because your length is increasing from L to L1. Okay, so this will be this would become integration of DL over L. So this will end up with natural log of your L. Okay, and because we are computing in between LO to L1, so this will be natural log of L1 upon LO. Okay, so I hope up to this it is clear to all of you how we are computing your ending strain in the case of your tensile test. Okay, so I think this we have already discussed. That is the curve, how we can compute your true strain on strain curve. Okay, so I will not repeat it. This is also we have discussed that when because we get your in your plastic region, what we get some flow curve sigma equal to K epsilon raised to the power n, and when we take natural log of this flow curve, this leads to a straight line. Okay, so this is natural log of strain, and this is the plot against the natural log of true strain versus true strain. Okay. So let us try to understand the volume consistency constancy during your plastic deformation. Okay, so let me uh, finish in next 10 minutes. After this topic, I will close today's lecture. Okay, so volume consistency, uh, because during the plastic deformation we have uh, your metal strip, and its volume is not going to change. We are aware. So during the plastic deformation, since it is caused microscopically, either by the slip or twinning of your atomic layer. So what is slip or what is twinning, we will discuss in the next class. If maybe you are aware, and that is why I have put this term in your material science course or manufacturing. You might have studied, but we will also take up this what is plastic deformation, how this plastic deformation takes place by slip or twinning of your atomic layer. These operations do not change the volume of your metal, which would require a permanent change of lattice dimension. This fact that the volume must remain constant during plastic deformation has also been observed experimentally. Okay, so let us take one example where you are having your initial, metal block which is having the dimensions A0, B0, C0. Okay, and it is being converted to the another shape and size. You are increasing your length, that is A1. You are increasing the width, that is B1, and you are decreasing the thickness or the height of your metal block, which is the C1. Okay, so with the with the concept of volume constancy, we can say VO, your initial volume of your metal block, VO is equal to V1, that is final volume of your metal block. Okay, so we can write VO is equal to V1, or in terms of dimensions, we can write AO multiplied by BO multiplied by CO is equal to A1 B1 C1. Okay, so this is quite obvious. Maybe you have done it in material science if there has been any discussion on elastic plastic strain. Manipulate both sides. Take in one side, you will get 1 is equal to AO upon A1, BO upon B1, CO upon C1. Okay, so this is you can write a natural log of 0 is equal to, if you take natural log of both sides, this will be sorry, by mistake I have written the A1 B1 C1. It should be in upper side. Okay, so okay, so let me let us not get confused using this slide. So let me write it again. This will be okay, I will change this slide. There is some typographic error, because this should be A1 upon A0, B1 upon B0, C1 upon C0. Okay, similarly here also, let me come here. Okay, so this is A0, B0, C0 is equal to A1, B1, C1. Okay, so this will be A1 upon A0 into B1 upon B0 into C1 upon C0. It is equal to 1. Okay, take natural log of both sides. So this will become natural log of A1 upon A0, B1 upon B0, C1 upon C0 equal to 0, because natural log of your 1 would be 0. Okay, so this will be natural log of A1 by the properties of your natural log. This will be A1 upon A0 plus natural log of B1 upon B0 plus natural log of C1 upon C0. This would be equal to 0. Okay. So what does it representing? Let us try to see how we calculated your true sin. It is natural log of L1 upon LO. Okay. So we can say that elastic strain in the case of considering your volume consistency, this will be epsilon A, that is in A the x direction, epsilon B, epsilon C is equal to 0. Okay. So during the volume, from the volume consistency, we get very important relationship, that is sum of true strain in all three direction. It is equal to 0. Uh, so what does it mean? Suppose there is a increase So what does it conclude? That if your epsilon A is positive, suppose it is having positive value, epsilon B is also having positive value, then obviously your epsilon C, that is the elastic strain in your C dimension, it would have negative value. Okay, so that its total sum is equal to 0. Okay, so we can observe this also from this particular diagram, that here we could observe that there is an increase in length as well as width, but there is reduction in your height of your metal strip. Okay, so for today I will stop here and I will upload the corrected PPT also. I will correct it, and